Hello, thank you for the introduction. It's an honor to speak to you all today about tunable neural networks for multi-material image formation from spectral CT measurements. First, I'd like to thank my colleagues from the II lab at Johns Hopkins, our collaborators, and funding sources. Spectral CT systems use specialized instrumentation to measure not only the overall attenuation of an object, but also its mass attenuation spectrum. One of the most important applications of spectral CT is material decomposition, or quantitative estimation of basis material densities. So most existing clinical applications involve two material imaging with dual energy CT. This would include soft tissue bone decomposition to better visualize trabecular structure in bone, or quantitative estimation of contrast agent concentrations for CT angiography or bone tissue perfusion imaging. I also want to point out there's many preliminary studies on next generation clinical applications of spectral CT with 3 or more materials. So there's some promising new types of imaging studies coming in the future. And all of these clinical applications will benefit from new material decomposition algorithms that can improve multi-material spectral CT image quality. So an increasingly popular strategy to improve image quality is to apply deep learning. I did this little literature search and found out that now over 25% of CT engineering publications mention neural networks. These data-driven models are able to reduce noise, improve image quality in single energy CT by learning patterns from large databases of training images. And we'd like to apply deep learning to spectral CT, multi-material imaging, but there's a few challenges. Some of those challenges are finding ground truth multi-material images for training targets, divining loss function to properly weight errors in different materials, and controlling the cross-material noise bias trade-off. So in this work, we'll generate our own spectral CT training data set using digital anthropomorphic phantoms and spectral CT simulations, and we'll apply neural networks to jointly denoise multi-material images. We also developed a new training method for tunable neural networks, which provides the capability to control the relative emphasis on variance versus bias. And we'll demonstrate how tunable hyperparameters can be used to control this variance bias trade-off in multi-material imaging. Our approach is based on a probabilistic model of image formation, where the patient, the measurements, and the reconstructed images are all modeled as random variables. So to model the distribution of patients, we use XCAT to generate a population of digital phantoms with randomized anatomical parameters. We have 3 basis materials: water, calcium, and gadolinium. Gadolinium represents portal venous phase contrast enhancement. And we extracted 10,000 2D slices, the level of the liver. For data augmentation, we applied some random scales, shifts, rotations. And this animation here is also showing the virtual monoenergetic attenuation images at 70 keV. So next we use spectral CT physics simulation to generate measurements with multiple noise realizations. Our approach can apply to any spectral CT system, but for this demonstration, we just chose to simulate an ideal photon counting detector with energy bin thresholds at 40, 60, and 80 keV. We generated 32 independent noise realizations for each case. So then we applied maximum likelihood model-based iterative reconstruction and material decomposition. This is a one-step statistical estimation algorithm to estimate the basis material density images directly from spectral CT data. And finally, we applied a convolutional neural network to reduce noise. So the network input are the maximum likelihood material density estimates, and the training target are the ground truth digital phantoms. It's important to point out the network inputs are 3 material images. So there's 3 channels on the input, and the materials are jointly processed, sharing information between materials to produce 3 material output material density estimates. The case we're showing here was trained to minimize mean squared error. So you can notice the network was able to reduce noise, but at the cost of some bias, both in the form of spatial blur, but also cross-material biases. The goal of this work is to develop a new training method to control this multi-material noise bias trade-off. Classic approach to training a neural network is to minimize a loss function like mean squared error. And we can show that mean squared error breaks down into equal weights on variance and bias squared terms. Bias here just means expectation of error, or the mean response minus the ground truth. So our proposal is just to modify this loss function with explicit weighting matrices on covariance and bias. And what this allows us to do is control the relative penalty on specific aspects of image quality. We originally presented the single energy version of this training method at SPIE this year. For background, I'll show an overview of the single energy version before jumping into the multi-material case. So in terms of practical implementation, what we do is use batches of multiple noise realizations during training, and then we can compute the sample mean across that batch of noise realizations and the sample covariance of the network output in order to implement this custom loss function using the predefined weights WCB and WC and WB. So you can see here the mean response is calculated from those multiple noise realizations. Mean response minus the ground truth is bias, and we also compute the sample covariance. And then, of course, we train with multiple patient samples to minimize the expectation of this WCB loss function over the patient population. So here's a simple choice how you can parameterize these weighting matrices just as scalar matrices with one parameter alpha. And this parameter alpha just controls the relative emphasis on variance versus bias. So we use this to demonstrate a new level of control over neural network output image properties. If you look at that center image, it looks familiar. It's trained to minimize mean squared error. A lot of people think it's over smoothing the image. So what you can do is turn up alpha. You're basically placing more of an emphasis on bias, and you have this low bias deep learning protocol. In general, though, WC and WB do not need to be scalar matrices. They can be any general matrix operator. And so if we take the singular value decomposition, you see that the right singular vectors are orthogonal features in the image domain, and the singular values are penalty strengths. So what's really exciting about this is it's basically a design space that you can use to with a lot of freedom to control neural network output image properties. What we've done in the past is used Fourier operators, spatial frequency domain weights. In this case, we used a Laplacian operator, a high-pass filter, to penalize high spatial frequency bias. And this is a way to control spatial blur. Spatial blur is basically systematic underestimation of high frequency signals. So it's a high frequency bias. So by increasing the penalty on high frequency bias, we're able to increase spatial resolution. And we can also use covariance weights to control noise texture. For this example, we used a mid-frequency bandpass filter as a penalty. And then we computed the empirical noise power spectrum, showed that there's this notch in the mid spatial frequencies. If you look at that bottom right signal, it still has low frequency noise. In a uniform patch, it still has high frequency noise, but the mid frequency texture is gone. So in this work, we want to apply tunable neural networks to spectral CT imaging. But for the multi-material case, things get a little more complicated. In addition to the cross-voxel noise correlations, we also have cross-material noise correlations. And if we train the joint material denoising network with mean squared error, we also see these cross-material biases, which may not be acceptable for a lot of applications. So if you use a static loss function like mean squared error, you kind of get what you get. You don't have control over these multi-material variance bias trade-offs. The goal in this work is to apply these tunable neural networks to control these multi-material variance bias trade-offs. Right. To this end, we used block diagonal weighting matrices. So we applied the same cross-material blocks to every voxel, and I'm showing those cross-material blocks. First step is to multiply each material by its mass attenuation coefficient at 70 keV. So the penalties are proportional to attenuation rather than density. And these are physical constants, so these are not tunable hyperparameters. Next, there's this 3 to 4 matrix. This the first 3 rows are staying exactly the same, but the 4th row is now a sum of attenuation from all 3 materials, otherwise known as a virtual monoenergetic attenuation image. And the next matrix has a hyperparameter alpha for each channel, including the 3 materials and the monoenergetic image. And these control the relative emphasis on bias versus variance in that material. So when alpha is close to 0, there's a higher penalty on bias and a lower penalty on variance. When alpha is close to 1, there's a lower penalty on bias and a higher penalty on variance. So if you want, you can think of these alphas as like a denoising level, and 50% would be the mean squared error case. Finally, there's another set of hyperparameters beta, which control the relative emphasis on different materials. So increasing beta for one material places higher penalty on errors in that material overall, including both bias and variance. So this is a 8-dimensional design space already. There's tons of things you could do just with this very simple parameterization. And we're just going to show basically some 1-dimensional sweeps. So we'll look at some examples. The first column here is the ground truth. The second column shows maximum likelihood model-based material decomposition. This is the network input. The third column shows network outputs when the network's trained to minimize mean squared error. And the fourth column shows the output of the tunable neural network. So for this case, we have alpha is equal to 0.5, which means equal weights on bias and variance. And betas are all equal to 1, which means equal weights on all materials. And the value for beta in the monoenergetic is 0, so we're not explicitly penalizing errors in that image. We're only penalizing errors in the material images. So this setting is mathematically equivalent to mean squared error, and so you can see the similarity between the third and the fourth column. But then, now we've changed alpha gadolinium to 0.1, and suddenly we are prioritizing low bias in the gadolinium channel specifically. And we show that by sweeping alpha gadolinium, you can control this variance bias trade-off. This particular parameterization is going to intersect mean squared error at this point, but you could have a low bias version. Here's another protocol. This is an overall low bias protocol where all the alpha values for all materials are set to 0.1. So you can notice that the neural network outputs are now more similar to the maximum likelihood estimates, which are also high noise, low bias. And again, as we increase alpha gadolinium, you can control the variance bias trade-off in just that material. One thing to notice about this protocol is as the bias in the gadolinium channel goes up, you also see a bias in the virtual monoenergetic attenuation images because it's directly constructed from a sum. So the bias in gadolinium is creeping its way into those attenuation images. Here's a different protocol. And the change here is that we've increased beta to 10 for gadolinium and the monoenergetic attenuation image. And so we're emphasizing errors in the gadolinium channel, errors in the monoenergetic image. We're penalizing those errors heavily and de-emphasizing errors in the calcium and water channels. Now, as we sweep alpha gadolinium, we still see this variance bias trade-off in the gadolinium channel, but now there's this compensatory negative bias in the calcium channel, which serves to maintain low overall bias in the virtual monoenergetic attenuation image. Okay, here's a quantitative summary of the same results averaged for all patients in the validation data set. We're showing those 2 protocols, which both represent 1-dimensional hyperparameter sweeps of this alpha gadolinium parameter. The main difference is that protocol B has this high penalty to discourage bias in the virtual monoenergetic attenuation images. For both protocols, you see this trade-off between noise and bias in just the gadolinium channel without much effect on noise in the other channels. For protocol A, increasing the bias in the gadolinium channel leads to this linear increase of bias also in the attenuation images. But for protocol B, there's lower bias in the attenuation images at the cost of this compensatory bias in the calcium channel. So this is a preliminary study to demonstrate the capability to apply tunable neural networks to multi-material image formation from spectral CT data. We showed that we can use these models to control the variance bias trade-off in individual materials, as well as preserving low bias in combinations of materials like virtual monoenergetic attenuation images. In the future, we want to use these tunable hyperparameters to optimize multi-material image quality for specific clinical tasks to improve clinical outcomes. Thank you very much.
Paper is open for questions.
Thanks, Matthew. I love this talk. So how important is it that you use the MSE loss function? Because you use a very particular decomposition of the MSE, but do you see any way at all to generalize this to other loss functions?
Yeah, that's a great question. I've thought about this recently. I mean, one very quick way to do that mathematically is to just take the L2 norm and just leave that as a parameter, and then you could at least include mean absolute error as well. So yeah, there's a lot of different ways this could go, and I agree it's a little bit of a constraint that we're basing this on MSEs. A lot of these principles could probably apply to other loss functions too.
Thanks.
This is probably a related question, but these networks are highly nonlinear, but you seem to be showing a fairly sort of linear response as you adjust these parameters in a systematic way. What insights does this give you, and how you might actually break that trade-off to sort of get better results in certain cases?
Can I ask, what do you mean by a linear response in what exactly?
Right. So when you adjust your parameters there, you actually see sort of a systematic change. It's not like, you suddenly get to a certain version of the parameter and suddenly there's a big step or something like that, because it can't compensate for your errors in any way. I'm wondering if this tells you something about how to sort of break those trade-offs and maybe improve your performance even more.
Yeah, that's a good question. I don't know if I have a great answer to that. The only thing I can say is for very small changes in these hyperparameters, the training loss function is almost the same. So, the optimum point would be pretty close for 2. I don't know. I mean, the bias, for example, is not exactly a linear relationship here. But yeah, I think there's a lot of it's a complex trade-off to explore in the future.
All right. Yeah, this is really great work. Please keep it up. Thank you.
Yeah, nice work, Matt. This is really about your future work, Bill, I think. Have you gotten any feedback yet from any clinical specialists about where they want alpha?
That's a great question. I have not. If anybody would like to give some feedback on that, I'm more than happy to hear it. But yeah, this is still in its preliminary stages, but I would like to really, I mean, I see this as giving us a design space, bringing back some actual engineering to these machine learning algorithms so we can control image properties. And it's going to, like we saw earlier today about, task specific objective image quality optimization. That's where I see this going, is picking some specific tasks and optimizing the image quality for those tasks.
Okay, we'll look forward to that. Thanks.
I want to follow up on this. So obviously, if I look at your work here, you can change the CT values of any of these images arbitrarily. Either you demand a low noise, then you get a bias. We don't know what the quantitative values of the image mean. Or you demand that you have a low bias and then you have a high noise. So this is a little problematic, I think. So maybe one solution around it would be to do what people do today. They do a frequency split. So basically, you do a reconstruction with your ML algorithm or with alpha equals 0, and you get a noisy image without bias, you smooth this image, and then you do the corresponding high pass filter on the other image that has low noise, and then you add these two together, and then you would have an image that has no bias and low noise at least in those lower frequencies that are of interest to do quantitative evaluations. And then you would probably get around choosing alpha and beta. You would set alpha to 1, I guess.
I think I see what you mean. Yeah, that I would like to explore that in the future, definitely. Yeah, I think one thing to say is, yeah, I think you can show mathematically that the maximum likelihood estimate under certain conditions is an efficient estimate. It achieves the Kramer-Rao lower bound for the covariance of unbiased estimators. So if you want to do completely unbiased imaging, I think maximum likelihood is in some sense the best you can get.
But we also want low noise.
But we would also like low noise. So that's kind of the idea, is you can't have both. And yeah, I appreciate the suggestion on the frequencies.
I think you have to do such tricks when you want to go into clinical routine. You cannot offer a slider that tells the radiologist either noisy or the CT values are wrong, or with correct CT values or wrong CT values and low noise.
Yeah, that was the motivation for this this second protocol that tries to strongly penalize bias in those attenuation images, because I can see why that would be just completely unacceptable. If in the monoenergetic attenuation images, the CT value was changed, it's not going to be all right.
Mm-hmm.
Thank you.
I just have one quick question, then we probably need to move on. I just wanted to clarify on the algorithm side. So you're doing maximum likelihood, then switching over to CNN. So are you doing your maximum likelihood in a different way than you would if it was just pure maximum likelihood? Like, do you truncate the iteration or anything like that?
It's the short answer is no. We're trying to ideally, we would like a converged maximum likelihood. We do have some limitation. I mean, it's the convergence criteria is just a maximum number of iterations. For just, this is a lot of data that we're processing. So just for purpose.
Okay, thank you.
Yeah.
All right, let's thank the speaker one more time.